Hello, my name is Oksana Pichugina. I am presenting today a talk, a performance comparison of unbounded Knapsack problem formulations. This is a collaborative work with two co-authors, Olha Matsiyb and Yuriy Skob. Combinatorial optimization problem is a branch of optimization that deal with finding the best solution among finite possible solutions. Combinatorial optimization has a wide application in computer science, operation research, engineering, finance, and many other areas. Euclidean combinatorial optimization that we use in our research is a subfield of combinatorial optimization that deals with optimization of images of combinatorial set in Euclidean space and utilizing properties of these sets and their convex holes. In this paper, we consider and investigate well-known Knapsack problem, which is a classical combinatorial optimization problem where a set of items must be packed into a knapsack subject to capacity constraint. And the objective in the knapsack problem is to maximize the total value of items packed into the knapsack subject to the constraint that the total weight of the items does not exceed capacity of the knapsack, which are called capacity constraints. There are many variations of knapsack problems. I listed only 3 of them, which we use. First of all, the first one is a binary knapsack problem, 0-1 problem, which is classical variant of the problem where each items can be included in the knapsacks completely or not at all. The objective one is the maximization of total value of the selected items, and there is a constraint on the total weight of the knapsack. Constraint one. Bounded knapsack problem BKP is the variant of the problem where each item can be repeated, and there is a limited number of copies available for each items, and the goal again to select a subset of the items which maximizing objective 1 subject to constraint 1, and one more constraint which is limit the number of copies of each the items. And one more variant is unbounded knapsack problem UKB, where there is no limits on number of copies. Here there is a list of some application of knapsack problem. It is resource allocation, finance, project selection, cut and stock problem, sentence compression, like summarization, pivot selection, etc. Importance of knapsack problems is also can be seen from the fact that there are famous benchmark libraries where different knapsack problems for testing your algorithm are located. Among them is OR library, Operation Research library, Demasked Implementation Challenge library, Matsiyb, and many others. So knapsack problem is a well-studied problem, and there are 2 main groups of methods of solution of the problem: exact method and approximate method or algorithm. Exact method are linear IP or ELP, linear integer programming, which is common for solution of this problem. Then branching bound method, constraint programming, and dynamic programming. Approximate method is greedy algorithm. Heuristic algorithms, including genetic and other evolutionary methods. For our investigation and computational comparison, we chose two popular solvers. It's Gurobi and CPLEX. These are actually solvers that are intended for solving linear optimization problem, mixed integer programs, and constraint and objective function are limited by polynomial of first or second degree, so can be a quadratic or linear program. There is a list of the features of these two solvers, who is developer, and etc. All this, both of these solvers are free for academics. So we can use this free, even though this is commercial software. There are also this possibility to use this in Python, both of the solvers. And if to compare these two, some problems are solved faster in CPLEX, some of in Gurobi, but in general, Gurobi outperforms CPLEX. And directly about our contribution to Knapsack problem, we consider several formulations, classical and some others that we utilize and then compare. So first of all, we formulate this problem as unbounded knapsack formulation in the following way. We denote n as the number of items, vi and w, double I and vi weight and value of these items. C is the capacity of the knapsack, and decision variables are binary, and they form vector x1, xn, where xi is the decision variables, which takes the value 1 if the item I is included in the knapsack, otherwise it is 0. Objective function is maximize total value of the knapsack subject to constraint, capacity constraint, and our decision variable take any integer non-negative integer value, including 0. The model we further refer as UPPIP, so integer programming unbounded knapsack problem. We can reformulate it as a bounded in such a way that we can always find the value SU double W and round it to the take integer part and find the upper bound for copies of item I. And then when you found these limits, we can reformulate the problem as a bounded problem with these bounds and this constraint. So we replace our constraint on integer that this value are integer non-negative values to this constraint and get another problem. So this is closer to the previous, but it is a little bit more strong model. And next step, we represent this model as a binary knapsack problem, 0-1 knapsack problem of high dimension. For that, we introduce a multiset. So we take all the copies given number of copies of each of the item and form a multiset. So this notation means that double one is used k1 times, the same here, and we introduce these two multisets, which cardinality is equal to capital N, and then in this notation we can now introduce these two multisets. In this notation, a binary equivalent to our unconstrained knapsack problem is maximization of this sum. So formulate the problem in a high dimension space, subject again to constraint, capacity constraint, and binarity constraint for each of the variables, because now our variables yg is equal to 1 if the item G is included, otherwise it is not. So to this model we refer to as UKP001 KP1. And we introduce one more modification of the model based on the following observation. So if we take tuples weight and value of each the item, then and form a multiset where each elements is such a tuple, then we can order them lexicographically following this formula. And this formula means that if, for instance, we can order all weights non-decreasingly, and moreover, if the weights are equal, then the corresponding value are follow this rule. And this means lexicographic order. And this constraint adding to our model, we have another model. So to the previous model, we add this constraint, which reduces a little our search domain and come to one more model, which we refer to 1KP.2. And the last step of our research is a computational experiment. Computational experiment for comparison of these models and different solvers. So we generated randomly knapsack problems of dimension from 1 to 100 in the form of these listed 4 models. As solvers, we use CPLEX and Gurobi. The implementation was done in Python, and when we implemented CPLEX, we used the package docplex. So there is an outline of our computational experiment, how our instances were generated. In each of the dimensions from 10 to 100, we generated 100 instances. And then run and compare it, and main conclusion that since these models are very similar to each other, then on average, first 3 models behave approximately the same. Sometimes one is better, sometimes another, but on average we cannot find some top model and say that some of them is favored. But if we compare the last version is KP to compare it by KP1, then adding this additional constraint is fruitful and positively impact performance. And comparing these two, performance of this improvement is around 15% compared to this one. If we compare CPLEX with Gurobi, then CPLEX works worse, shown worse performance, around 20 on average. It is worse than Gurobi. Gurobi is champion. So to conclude, This research shows that different formulation of any combinatorial optimization problem, such as even this well-known Knapsack problem, results in very different results in different performance. So you can improve performance with choosing right model, better model, and also choosing better for this class of problem, better solver. So this means that there are many ways to improve performance and get solution faster. Thank you for your attention, and please questions.